I have some links for you all. I put them in the Discord. And I realize that some people maybe aren't on the Discord. And so for those of you who aren't, there's also a link right there to a tiny URL that will bring you to a Google Doc that also has the links so that everybody hopefully can get the links. So the tiny URL is just tinyurl.com/AstroEdUNC-HRD for HR diagrams. So if you go there, that will bring you, but if Discord is more convenient, then, because you've got it up, then you can go there too, but there's also this list of links. So we're going to do, I'm going to demo the whole thing, and then I'm going to get you to do some stuff. This Google Sheet, if you want to distract yourself as I'm going, no, you don't want to distract yourself. I'm not going to tell you what to do with that. I'm just going to hop right into it. So I need to, darn it, get away from that thing that sits at the top of the page. Okay. So HR diagrams, what I'm going to run through is image processing in Afterglow. We're going to actually have you set up some observations of a star cluster and build HR diagrams with whatever star cluster you decide that you want to observe. And so that's what this spreadsheet's for. And then I put a link to Aladdin Light in there so that you can search. And then, but everybody's allowed to choose one, set up an observation, and I've got some instructions on a tab that's now hidden right there. So we'll do that in a little bit, but first I'm going to, so you would set them up in Skynet, but I'm going to start by actually processing some images, show you what you can do with your images. So there is a sample set of sample images. I really recommend not trying to follow along with me because I'm going to go so much faster than you're able to. Or not, if I can't find the, sorry, sample MW, sorry, right there. And then here, and then there, and then individual images. So you set up an observation, you got your images back, you open them up, it takes a minute. Oh yeah, and the other reason why I don't want you following along is because we don't want to go through what we did yesterday and crash everything. But I never planned for you to try and follow along with this. You can do it on your own afterwards. Okay, so you've got these images. Here's some B images. There's 5, I think, that I took in each filter. Or a student in my class a couple of years ago did. Some R's, some V images. There was a peer flip, apparently. Anyway, so we're going to start processing these. The first thing that we need to do to process them is go to the WCS calibration tab, because these were taken a couple of years ago, and it took a while for us to realize what the problem was, but there was a bit of a mix-up with ones and zeros. And with the peer flip, we weren't getting images to align properly because of a mix-up with ones and zeros. That has since been corrected. However, I want to show you the WCS calibration tool. So you get your images, and there is a more accurate WCS algorithm so that we can actually get the coordinates of everything in the image. So you click on this to select all images rather than here and checking all those. And then you extract values from the current viewer. That'll give you the astrometric solver a good starting point. And then we click submit, and we'll get an updated set of coordinates for every image. This one actually takes the longest when I ran through this before. But you can see the progress down there. We're already at 35%. And once this gets done, this image is looking fine, but didn't I see one? This one has, there is a bad column in here. Yeah, Yeah, if I zoom in here, you can see there's this line and this bad column. We want to make a nice, pretty picture of this star cluster with this nice planetary nebula in it, and so we are going to correct that before moving on. It's important to do it before you move on, because once you've aligned and whatever, then the correction doesn't work. But we've got this cosmetic correction tool that will automatically correct all of those features, and you select all of the images and you leave all the default parameters as they are, and you hit submit. And zoom in so that we can see that. The telescope also needed to be collimated at the time, as you can see. Had a little bit of a bite out of the stars. We did eventually get that fixed. So one-click cosmetic correction, it looked at and it found that that column was brutal, and it just fixed it for us. So isn't that nice and magical? That's why there's this magic wand. Next step, go to the aligner, and we're not doing a mosaic. We just want to align all of the images. We want to align all of the images in all of the filters together, and it'll align using WCS. There are other options, but we want to use that accurate WCS that we just set up. We can select any of the images because they're all good in this data set, but you want to select a good image and then align them to each other. The aligner is pretty quick. Until it gets to 67% and just crashes. That's a weird thing there. Okay, so now all of the images are aligned, and now that they're aligned, we can stack them. We don't want to stack all of the images, though. We want to stack them per filter, right? So I'm waiting for this thing to stop doing what it's doing. Once it loads all of these newly aligned images, I guess is what the holdup is. People doing things rather than just watching. There. I just want to align the B images to each other. So I select all of the, so if you type B in this filter list thing, it'll filter and only show the images where they have a B in the file name. So that's convenient. So now I can select all of the B images. And then I'm kind of old school with this. I like just a median, so 50th percentile. Can leave everything else, and then submit. And we've got a nice stacked and aligned B image. So that's what that one looks like. We can do the same with V. I'm just going to do B, V, and R, even though I aligned I. I just need 3 colors. So, sorry, R. All of these images, the file name has R in it. So, oh yeah, right here. So, but if I go with R underscore, then I get the ones that have the filter R. So sometimes you have to add a couple of characters to that. But then submit. And then I want to combine those 3 images that I just made to each other. And so easiest way to find them is to type stack, and then the stacked images show up. Select all with this button. They're grouped together. And then once you group them together, they no longer say stack, I guess. And you're not going to have to do this stuff today. You're going to set up your observation today, and then I've got an instruction manual for you to be able to do exactly this with your images that you collect. But I want to show you the process. So there, now we've got a combined grouped set of images, and I want to make my B image blue, and I want to make my R image red. And that's how that's done. You just right-click on it, color map, and make it green. I promise you're going to have some fun here in a few minutes. I'm going to let you do things. So there's a combined color image. If I look at the image display, you can see that the histograms are all offset funny. And so the colors aren't right. And so what Josh has built is the ability to use photometry and colorize the images based on their apparent magnitude, in each of those filters. And so I need to link all the layers by their percentage value and then photometric calibration. And if I measure the image 0 points, then it'll come up with that. And I do this, I want to colorize them as if they were a black body that peaks in the B. And then I'll get a photometrically calibrated color. There's even the ability to subtract extinction coefficients so that you can see the star cluster in this case as if there were no interstellar medium, actually see the colors of the stars themselves, the intrinsic colors, but I don't know what that is, so we got to figure that out first, and then we'll come back and change that. So combine colors, and then here they're actually photometrically calibrated. I can make them really pop, though, if I change my stretch tone to this magical mid-tone one, hit the default. They pop a lot better there. I think background set to about 20 and maybe like 96 for the mid-tone level. And you can see that planetary nebula and the white dwarf and all of that. So that's the color image. So we've gone and made a color image. Someone was talking about how graphing is really important in astronomy, and that's one of the skills that we can teach people is to interpret and graph things. And a really good graph for star clusters that have colors and different magnitudes is a color magnitude diagram. So we could photometer these stars, and it's really easy. You go to the photometry tab. Oh yeah, but I can't if they're grouped together as easily. Oh yeah, I could. So we could photometer these. There's source extraction, extract all of the stars in the field with a click, and then I can photometer all of the stars. But we built a tool where we don't need to do that. And actually, we could just look up and use Gaia data, for instance. And so we're going to build a color magnitude diagram. And this is the thing that I'm going to demo for you that I'm going to ask you to do next. In my case, I used NGC 2437. And so I just click on, or I type it in here, NGC 2437. And I look it up, and its radius is 0.57. So if I test that radius, we have a limit of 5,000 stars because the graphical interface can't just, it lags if there are more than 5,000 points. And so I've got to reduce it, and I think 0.15 works. Yeah, I get 4,000 stars. I could maybe increase it to 0.16. Yeah, that's still good. Click next, and next, and it brings me to the next page. So one of the things here, or here, is all of these stars are not stars in this star cluster. So if we want to build our color magnitude diagram, we've got to get rid of all the stars here and analyze it. We've got to get rid of the stars that aren't actually cluster members. So I go here, and the way that this works is proper motion is plotted in these top 3 graphs. And distance down here, this is a placeholder, don't look at it. This one is the color magnitude diagram of everything that we're seeing. And so the way that we've designed this, the top bar is essentially a zoom feature. This right here in proper motion space, that's my star cluster. It's moving differently from the Milky Way stars that are in the field. And so if I zoom in on that cluster, it automatically cuts out everything, but I can also use this slider down here to cut out everything that's outside of that. Zoom in on this, you can see right away that the field stars are being removed from the color magnitude diagram. Zoom in on this one here and do some cuts. And then I've got my distance, and I want to zoom in on distance. There. Something like that. But remember, we didn't get all of the stars in the cluster. We went to a limited radius from the center of the cluster, and that's where we fetched the data from. And so we've got this archive fetching page, and I can add in catalog stars, and it was 0.57 was the catalog radius for this cluster, and so the default number here that you see is double the catalog radius, and we can just fetch all of the data from all of the all-sky catalogs that exist in optical and infrared, and test it, and see if we have fewer than 5,000 stars now because I did the proper motion cuts and the distance cuts, and I do. So then I fetch. We have a back-end catalog where we've already gone in and matched Gaia data to all of the photometric catalogs. So we have the distance or parallax and the proper motion values for all of the stars in all of those catalogs, and that's where these column heights come from, is because there are more stars in the Gaia catalog in this field and fewest in APAS, and because we're still at, Brian, DR9, and Brian just nods because he knows, and he knows I know, and we're not gonna, we don't know any more than that, right? No, no update on DR11. That's what I figured. So back to field star removal, and we can just tighten up those constraints, and like I can see the cluster here. Tighten up. Maybe a little bit more. Cut out those field stars in distance as well. Okay. So these are my stars in my cluster. Now I want to match isochrones to them so that I can determine how old the cluster is and what its metallicity is. So I'm going to build a Gaia color magnitude diagram. Say B minus R versus R. And this is NGC 2437. So if I frame on the data, or actually this is kind of neat. You can, if this standard view frames on the isochrone model. So we can dynamically change the isochrone model, like say change the age, and you can just use this to teach how the turnoff point, say, moves down the main sequence as the cluster gets older and older, or how the main sequence actually drops down to the red dwarfs drop onto the zero-age main sequence as the cluster gets older, and they take longer to reach the zero-age main sequence. That metallicity, as you increase it, has a significant impact on the places that stars exist on HR diagrams, even though our intro astro textbooks don't use the word metallicity or say anything about the effect of metallicity on stellar evolution. It has an enormous effect. Yeah, so we want to actually fit this. So let's frame on the data and do some fitting. It could be something like that. It looks like I'm out in reddening. Maybe the metallicity is a bit low. Something like that. Age looks like it needs to, that's too much. Something like that. And I've just matched the isochrone to the main sequence. This cluster has a bit of scatter in its main sequence, but sometimes some clusters that you'll see, there are stars that sit above the main sequence. That's because they're unresolved binaries or unresolved doubles anyway, and so they have, say, the same color but maybe double the luminosity, and so they exist above. Got these giants over here and my turnoff point, and I've estimated very quickly and crudely, without spending too much effort on it, what the metallicity and the age and the reddening of this cluster are. Oh, right, reddening. So I get an estimate of 0.16 magnitude. So then I can actually go back to afterglow and say, zoom in a little bit so that we can see some blue stars. So here you see that these are quite white. We want to remove the reddening from the image. So if I went back to that show display and photometric calibration, and I plug in 0.16, calibrate colors, and maybe the colors got a little bit redder. Yeah. Oh, I percentile linked. Darn. Ah, okay. Can I link by pixel value now?
I think so.
Okay. Photometric calibration. Do I need to do anything other than just that? They do look bluer on my screen. They do to you too. Oh yeah, right. If I went back here and set that to 0, let's see if it, oh yes, they really got quite white there. You can save a screenshot of this and actually compare the two side by side. 0.16. Yeah, to me, it's pretty clear that these ones are bluer, where I've removed the reddening, and these are nice white stars. This one, I'm guessing, is probably redder than that. Can't see it too well. The white dwarf went from being quite white. It's got a more of a bluish tinge to it. So anyway, that's for a reddening value of 0.16. So you can imagine that it gets quite dramatic if the reddening is more like 0.5 magnitudes or something like that. So that is the tool and the observations in Afterglow. Now, we have this instruction manual that we have built, and essentially this is a crash course in stellar evolution that sort of, it walks through all of the features of all of the aspects of stellar evolution that are really needed to understand all of the features of the HR diagram. So you actually I give this to my students, and they work through these examples, and by working through these examples, they learn a lot about, and there's some videos as needed. and yeah, work through and understand, because there's too much. You can't just show someone one cluster and say, here, now go and do the analysis for another cluster, because every cluster that you do is going to be different. It's got different aspects to the field star removal or the way that you fit the isochrone model. And so there's a fair bit of deep learning that has to happen to be able to actually use this tool. It's not just a trivial tool to use, but it's quite a handy and powerful one. Once you're done the isochrone matching, oh yeah, there's the ability to say, use those APAS values. We could plot B minus V versus, say, I prime. Add that one in, and it just shifts over, and we've got our APAS values. I'm not sure that I trust that. It could be that my model is off, or it could be that the calibration is not perfect. I could also plot some WISE data, or W1 versus G prime versus K, and throw that one up, and it looks like that, because I went infrared minus blue. Anyway, so yeah, so you can build your HR diagrams however you like. And then there's a results summary page. And so this sort of summarizes where the cluster is in the galaxy, plot another HR diagram. There's a number of derived quantities, like from the velocity dispersion and the radius, because we can calculate the half-light radius quite easily on the back end. Using virial theorem, calculate the mass, the virial mass of the cluster. So there's all these features and some charts to sort of see how this particular cluster stacks up against the rest of the clusters. We created a catalog because what we were finding is that a lot of the clusters were able to fit models and determine parameters seemingly better than what's in the Milky Way star clusters catalog. So we built this thing. It's kind of acting slow, and I don't know. This is version 0, and I'm not going to show it off because it might not even open. But yeah, so there's these instructions that you can use if you get hung up. You're not going to be able to use them today in the workshop. We'll see how well we do with the workshop. I did want to mention that the instructions don't currently have observation instructions and all that for using LCO, but we plan to build that in. So there are instructions for setting up observations in Skynet, but say the high school teachers here, if you end up with some LCO time, then you could do this. We have built, using the API, having trouble with the LCO API linking it in and being able to use the data, but there is the ability to download data and import and whatnot. But so that's a possibility. And then the other thing that I also wanted to quickly mention, because I know that Edward set the deadline for the Global Sky Partners, which is LCO's, I don't know, maybe Lisa wants to say something about it, because I don't know enough about a Global Sky Partners program, but the deadline for applications is coming up like the 19th or something of this month. Am I right?
I don't know, but I think that sounds about right.
But people were talking about doing education research in the last session,
Yeah.
and there are high school teachers here and people who work with high school, so I think it's a good moment to just ask you to say something about Sky Partners.
Yeah, the Global Sky Partners is our current flagship education program at LCO. And what we provide is telescope time, technical support, and a community to be part of other educators, while you run your own education program for whatever that uses our telescope time for whatever group you're working with. The program is global, but being, if you're based in the United States, that's not necessarily a disadvantage. That includes the global audience. And it runs from Rachel and Calais are both Global Sky partners. Actually, you might actually want to talk to them for the real skinny on how things work. But any program is, it's what you want to do. It's not necessarily what we want to do, but you want to do for an educational program. We have, students doing original research. We have students who don't know anything about science doing the double star program and learning that they can do science. We had an organization, they took a picture in North Carolina, actually. It's called Star Song, that they took images of variable stars and then they plotted them on a clef and they sonified it. So they played their variable star. So, and we have somebody taking telescopes to Ukraine. So it's a very broad program. And Edward Gomez is our education director. He gets back from vacation tomorrow and would happily answer emails about it. And I will as well, or answer questions if anybody has any questions.
Thanks. Yeah.
It's actually my project. Yeah, the Appalachian Sky Star Song project. Yeah, that was mine. Yeah, that's mine. So just in a nutshell, particularly doing outreach for K to 12, LCO I think has it just right in the design of the kiosk, which is their online-based platform for students, particularly elementary schools students, but also middle grades can actually do that submission, and it's very streamlined, right? It doesn't have all the bell and whistles that, for instance, Skynet does. It could, right?
They're
it could.
hidden, yeah.
But it's been very useful, and in terms of public engagement through K to 12, getting those robotic telescopes into the classroom, I think that is a really good program. And anybody who does any kind of engagement through K to 12, I highly encourage. And also in terms of engaging amateur astronomy clubs in the community, if they want to give a shot at using robotic telescopes, that is also a good entry place to do it. So that's my 2 cents. Thanks.
Thanks, Enrique. Yeah, so clusters, and back to this, the submission failed, so we're not doing that today. How much time do we have for this session, Reed? Dan? We got half an hour. I'm going to then, just before we get working on it, we're going to have our other project that's going on. Where's Ahmad? Oh, he's not in here. Then I'm not going to say much about it. We can talk about that later. He's busy working on a proposal right now for Dragonfly. So yeah. So, and that's where we started doing this thing with this collab, which does a lot of those features, like the proper motion, RA deck plots. Reed sort of whipped this up on Friday, and then we've been tinkering with it a little bit since then. He made this graph, which is really cool. So the idea behind this AstroCodex collaboration is building a sort of a living repository for computational astrophysics, workbooks, that education resources that people could use. And so Ahmad started this with a one-day hack day conference at Yale on Friday, and that some of us were at. And so we're excited about that too, being able to sort of go beyond the fixed platforms that we have to maybe doing other things. Like we can already download data. There's a lot that can be done, but there's more that can be done with a project like this. And so having things built in a Jupyter notebook, and here I've used Google Collaboratory, but we're talking about other platforms that would be better, that are still accessible, and intro students don't have to download a whole bunch, but they actually can see the Python code, which is a useful thing that we can teach with astronomy. Anyway, let's get you all working. there's this list of June open clusters. I don't know if you want to do this right now, or you could submit your observation later on, but please submit an observation for a cluster. I set we've got 59 or so, 58 clusters that should be observable right now, and we've worked out some exposure times with different filters that should work pretty decently. Minimum field size that you want to use, and then just some basic instructions for setting up the observation on Skynet. So here are the fields of view of telescopes that I would recommend using, and you've got a minimum field size that would be probably recommended for this. You could also access Aladdin Light and actually look up NGC 4103 and see how big it is in Aladdin Light. It is a smaller cluster, 21, yeah, maybe we can see it. Yeah, 10 by 10 field should be decent, but maybe a 20 by 20 would be even better, and you might get a more spectacular picture. So you could decide which telescopes you would want to use to observe whatever cluster you decide to observe. I would suggest selecting at least, well, you have to select at least 3 color filters, BVR, G prime, R prime, I prime, or whatever combination you like. Make sure when you're setting up the observation to set your telescope efficiency to generic. And the last thing that I want to say here is, so you want to schedule at least 5 images, and you want to make sure that when you select the observation, I'm going to say schedule as an image sequence and continue the sequence on the same telescope, so that if you take a picture with one telescope, you continue using it. But what I suggest doing is not just taking 5 images back to back, but taking them with an hour apart. And the reason for that is because sky conditions can change, and you can maybe get a better observation later on and a worse one. And it also, because you're going away and coming back, it automatically dithers your images for you. And so you can align them and get rid of any effects in the field in the image. So those are the basic instructions for setting up the observation in following sort of and all these instructions are in this once you sort of go down to the observation bit. There's even a table with images of those clusters, although I would just use Aladdin Light. And then I've got exposure times here for you to use for those clusters. So you could set up the observation, and then whatever cluster you choose, look for one, decide on one with Aladdin Light, and then you can go ahead right away and analyze that cluster's HR diagram with ClusterMancer. And so just type in the cluster and start going with field star removal. So I would recommend people focusing on this. Just choose a cluster that you want, and then go to ClusterMancer. Leave the observation set up for later, because you got some help with that yesterday, and you might want some help with things like field star removal and all of that today. And so for the next, 25 minutes we've got remaining, just walk around, and Kaleigh's going to help, and I think that Dan's going to help, and Ian's going to help, and Art. Oh yeah. The tiny URL was on Discord. Yes. There. Right there.
Just a quick remark on using ClusterMancer before we get started. So it's pretty computationally intensive on your computer. So make sure you don't have too many tabs open. Just make sure you have a smooth experience.
I got it. Okay, let's give Daryl a round of applause. He's really spearheaded this. You know, we all teach HR diagrams in our introductory classes, and this is just an amazing tool. You don't need access to a robotic telescope. You can just plug and play with a little bit of practice. Okay, last activity, and then I'm going to let you go. We need to pick our dangerous questions. The one that, we've started the conversation